Hello, this is Michał Wójcik here, and I welcome you to the series of my lectures, Physics for Amateurs. On our last lecture, we introduced the concept of matrices and vectors. There were column vectors and row vectors. Today, we will build a bit on these concepts. Matrices and vectors, and especially multiplication between matrices, can be used to simplify a lot of equations and to remember them in a very concise form rather than complicated summations, etc. But to do this, we need to rehearse matrix multiplication, and we do this in a way now in which we will write matrices in a bit more generic form, and we will also use sigma symbol for summations just to get used to it. So let's start. Let's assume we have two matrices, A, which we will note now in a very arbitrary form, so that will be A1, 1, A1, 2, and here we will put some dots to denote that we will continue this till some n. Now, we will have some, let's say, row 2, so there will be till A2n. And now we will continue to the row m. I think conventionally, let's allow me to reverse it. We will go here to m and here to n. We did it just because there is a convention to use nm rather than mn. So n is number of rows here, and m is number of columns. So the dimension of the matrix is like this. So now let's. So that's matrix A. We want matrix B, by which we will try to multiply. So we will try to do multiplication A, B. What is important now, columns in B needs to have the same length as rows. So B1, 1, but we need to end here with BM1, and let's say we will the number of columns is arbitrary, so we can continue till let's say 1p. P will be our number of columns. So here we have, very often we will write only 4 just to denote 4 corners to denote, but for now I'm just trying to be a bit more verbose. BM2 and BMP. So B has dimension m times P, where this is number of rows, this is number of columns. So now we can do multiplication. The purpose of this, of writing this, was that now we will try to write matrix multiplication using sigma sign. Let me move this AB a bit to the left. Right. So AB, and we will think what will be in I row and J column of the matrix, which is a multiplication of those two. So remember, we need to take if ith row and jth column, multiply relevant elements and add them all together. So we will be adding over index k. Now k row from A, column from B. So we will iterate k from 1 to m, because this is the length of row in matrix A and length of the column in matrix B. And now A I k times B k j. Once again, we have chosen ith column, ith row from matrix A, and jth column from matrix B. The number of row is the first index, the number of column is the second index. So this makes sense. That will iterate over ith row, that will iterate over jth column. And we multiply and add all them together. So this is a symbolic way to define matrix multiplication. In fact, that might be our definition, but what we say about rows and columns is only our technique to memorize it. That might be the definition, and we might try to understand this definition just by talking about rows and columns. Nevertheless, we used this to make us more familiar with this kind of symbolic notation. If someone wants very much, we may rewrite it in a way which almost explains what sigma is. Now it is quite obvious that we are summing from 1 to m without writing a sigma symbol. But obviously this expression is shorter and in fact more precise, because someone might ask, well, I don't know what really is in place of these 3 dots, because with that kind of denoting things, we need to count on readers' intelligence to understand what we meant. And mathematics is all about to avoid intelligence. No, I'm kidding a bit, but to some extent this is true, because we try to, in mathematics, we try to decompose our reasoning into the smallest steps that someone could follow without any intuition, any deeper understanding, just step by step. If the steps are correct, then the reasoning is correct and we have proof of something. So there is a lot of depth in saying that we try to avoid person's intelligence to try to guess what these 3 dots mean. This is a straightforward algorithmic way to write it, so no one needs to think to match what that continuation might be. Right. So this is matrix multiplication, and we will be using it later. I mentioned a few operations that we can apply to matrices. We can obviously add matrices, and we can even here write in a similar way what does it mean to add matrices. This is obviously adding element from the first one. Sorry, this is plus here. This is obviously adding elements from the first and the second. So ith, jth element of the matrix, which is a sum of 2 matrices, is just the sum of ith and jth element of matrix A and ith and jth element of matrix B. So we can add matrices, we can multiply matrices, we can take transpose of matrix like that. There is one more very trivial operation. It almost doesn't need to be mentioned, but you can multiply matrix by value. So if you have a, let's say, the smallest possible, well, not the smallest possible, but the smallest which kind of represents the idea of matrix rather than vector. So we can multiply matrix by number, and that simply means we multiply each element. But this is important bit, because when we can add objects and multiply them by a number which might be real number or complex number, and they satisfy some usual conditions that we require for summation and multiplication by number, they form a vector space. So if you if you think about vectors, you think about, well, first about some directions in space, directions with length in space, but obviously the space might be multidimensional, as in mathematics we very often have it multidimensional. But in a very general way, vector is anything that you can add together and multiply by real or complex value, and which obviously satisfies certain natural laws for this summation and multiplication. I will not elaborate now what are these laws, because that's not the purpose of this lecture. I'm only signaling this, that if we think about matrices, vectors in notation column or rows, with summation and scalar multiplication, they all form vector spaces of a particular dimensions, and these dimensions in case of matrices are simply n times m, where n is number of rows and m is number of columns. So the dimension of space of matrix which are 2 by 2 is 4. The dimension of matrices which has only 1 row and 3 columns is 3, etc., etc. But this is a bit of diversion from the main subject. The most important for us was to summarize the operation on matrices in a bit more abstract way. Now, having that done, we can go to functions. In mathematics, there is a way to denote a function, to write a function, which establishes a domain and a space of values of the function. So here we know that function f will take value, real value, and transform it into another real value. So for example, f of t equal to sine of t is an example of this kind of real value function from real argument. If we can write something like that, the g is a function of r square, and transform pair of real numbers into numbers. So simplest example might be x plus y. This is an example of function which acts on pairs of real numbers and returns a number. But in physics, we usually forgot about this notation, and we rather think that we have something like value u, which depends on t, and in that sense u is a function of t. If we have, for example, a function v, value v, we will a bit use them interchangeably. If you have value v which depends on x, and then x depends on t, we write it in a way sine of 2t if we want to substitute, and then v depends on t. But obviously, if we write it in a way that this is a function v of x and this is v of t, it doesn't match, because v of x is sine of x. So if you substitute x here with anything, that thing will go here as well. So in that sense, v of t is sine of t. But for us, v depends on t in that way. So that's why in physics we a bit avoid this kind of notation. But we will also use it when needed. But we need to understand what we are doing. Why is that? The purpose is simple, because when we talk about any relations between variables in physics, any functions in fact, we think about some value which represents something real, something which exists in reality. And then when we express v as something which exists in reality, as sine of x, and x also exists in reality, but it happens that x is equal to 2t and t is also some value existing in reality, then v depends on sine of 2t is equal to v is equal to sine of 2t. And we are less interested in this original formula. This is not the formula which defines what v is. We usually know by some reasoning what v is, and we are finding that v is equal to sine of x, but also sine of 2t, because we know that there is dependency between x and t. So it is usually not like this, that one of these forms is the base form. It just depends by what we want to represent v. If we want to use x, we use this formula. If we want t, we use this formula. But there is nothing like a function which represents f, because function depends on argument. So v might be equal to sine of x, but also v might be equal, I will use s here, sine of 2s, when we think about t using argument in the bracket. So that's why we usually say that variable v depends on variable x, rather than saying that v is a function of x, because function will suggest this kind of mathematical formalism, which is not exactly suitable for physical needs. It can be used, obviously, but then everything will be longer and harder to write. And in physics, it's really important to make our notation as concise as possible. To give you an example, why is that? We will use exactly this. V is equal to sine of x, and we know that x depends on t. So when we calculate derivative of v with respect to x, it's obviously cosine of x. But if we want to calculate derivative of f with respect to t, we might use the equation which is called chain rule for calculating a derivative when we have function given by one argument and then this argument is expressed as the other argument. So that's simply derivative with respect to this argument times this argument expressed as value of t. Here this is t, but it might be any arbitrary letter, and then multiplied by this derivative of x with respect to t. So this is simple chain rule when we talk about one-dimensional dependence of values, because values might depend on many variables, so we will have then multidimensionality. But this is the simple problem. Everything has one dimension, so there is simple multiplication of derivatives, and now it goes like that: cosine of x times 2, because derivative of x with respect to t is 2, and if we want to express everything by t, it will be 2 cosine of t. Obviously, if we apply, if we write now v in explicit form, sine of 2t, and we will apply the rules of calculating derivatives, we calculate derivative of internal function, which is 2 multiplied by derivative of external function. I didn't substitute here properly because x is 2t, and we see that they are equal. So this is how chain rule works on example. We will not prove chain rule. We will just apply it. Now, we can have situation in which u depends on two variables. So now u is a value for which, to calculate it, we need two arguments, x and y, and only then we can calculate u. So we can think of u as a function which maps pairs of real numbers to real numbers. Now, we can still calculate derivative of u. But now, this is quite symmetric if we think about x and y. So we can calculate derivative both with respect to x or with respect to y. And we will denote them in that way. This is how we denote partial derivatives. So derivative of u with respect to x is 2x, because this is derivative of x squared, and when we calculate derivative with respect to one variable, all others are treated as constant. So the derivative of constant is 0. So that's why derivative of u with respect to x is 2x. And that will be exactly the same, because situation is symmetrical, that derivative of u with respect to y is 2y. We can obviously complicate it, and we will in a few examples in a minute. But I will show something more here. I want to show something more here, because having u dependent on x and y, we might have situation where x and y depend on some other value. They might both depend on value t. When that might happen? If the point travels around some center, actually this is 0.00, in circle at some distance, actually at distance 1. It's equation of motion which looks like that. And now we have certain value u which we can calculate for each pair of real values, so we can calculate it for each point of the plane. Now we can calculate derivative of u with respect to t. So just treat it as, we can treat u as function of t, and we can calculate its derivative. So we can do this directly just by writing u as dependent on t, and calculate derivatives. So that will be here minus sine of t minus 2 sine of t times cosine of t plus 2 cosine of t times sine of t, which happens to be 0. So that simply means that when the point is circling, the derivative of u with respect to t is 0, and this is for a very good reason, because u is a square of the radius, and radius is constant, so u is constant during this movement, therefore its derivative is 0. But we have another way to calculate the derivative of u. We can use chain rule for a function of many variables. When function depends on many variables, the chain rule looks like this. We take each variable and calculate derivative with regard to that variable, and then multiply it by derivative of this variable as dependent on the argument t. So variable x with respect to t, and we add them together. So u depends on x and y, so we need to use x and y here. So now derivative of u with respect to y times dx over dy over dt. And just to make sure everything is in order, let's calculate derivatives. That's 2x. Now x, derivative of x with respect to t is minus sine of t plus 2y, because this is derivative of u with respect to y, times cosine t of t, because this is derivative of y with respect to t. Now, if we substitute x with proper expression, which is cosine of t, and y with proper expression, which is sine of t, we will get 2 cosine of t times minus sine of t plus 2 sine of t times cosine of t, and because here we have minus, we can extract it and put it at the beginning of this summand. That's equals 0, exactly as here, because that this must be the same value according to the chain rule. So just to rehearse this, if we had u which depends on 3 variables, like this, for example, but think about other examples as well. It might be x times y square plus z times sine of x. And now you have some dependency that x is some function of usually it is opposite, but usually this is opposite, but nothing stops us from having a situation where x is equal to sinus of t and y is equal to cosine of t. So that will be equation of movement of particle in space, and we have, it's just an example, can be really anything, and we have example values here which might depend. Obviously these are two separate cases, they can't hold together, but you might be expressed, you might be might depend on three variables like that, might depend on three variables like that. It's really up to our invention how it will depend on that variables. In any case, the chain rule is like this. We take each partial derivative, multiply it by derivative of argument with respect to our main argument, and add them together. So here we will have three summands in our summation, and derivative with respect to z times z, derivative of z with respect to t. This is the chain rule when we have three variables on which our value depends. It is pretty analogous, so if there will be 4 or 5 or n, we also need to calculate each of them, multiply by relevant derivative of the same argument with respect to t, and then sum everything together. That's a chain rule for multi-variable function. Now, it might be that we have values which already are, let's say, three-dimensional. We will know them in format of the column vector, but nothing stops us to denote them as this kind of brackets with tuple. It's just a convention which might be convenient in certain contexts. So now f is three-dimensional, and if you think about it, that might be force. That might be force, which is a vector in space. Now, force might depend on position. So we sometimes write this like that. That F1, F2, and F3 are some functions which depend on position in space. So we are talking now, in fact, about force field in space. If you know the force field, so if you know in which point you have what kind of force, you can predict the movement of the particle, because for each point you can calculate particle acceleration. Knowing its acceleration, you can, well, you need to know initial velocity at some point, but knowing velocity, if you can calculate acceleration, you can then update velocity in some small time interval. If you update velocity, you might update position. If you updated position, you can know what is the new force, new acceleration, and so on and so on. And then by numerical methods, you can try to calculate the movement of the particle. So this is the way how to understand that force given in each point of the space might tell you what will be the trajectory of your particle. So we might have this kind of force field, which is a function of three real numbers. Each of them represents coordinate in that case. But the values are also three-dimensional. So this is a function which has three real numbers as value and three real numbers as arguments. I will now change a convention a bit, and you will know why I'm doing this in a few minutes. Instead of talking about x, y, z as coordinates, we will use x1, x2, x3 as coordinates. In fact, we started this already with values. So the situation is the same. F depends on position. F depends on position. It's just that position is denoted using x1, x2, x3 rather than x, y, and z. And we did this for a reason. And we did this for a reason because now we want to introduce a new symbolism. We want to use variable x, which will denote for us three-dimensional value. We will speak value, but when we will put this into a function, it will become argument. It's just it just depends a bit on context. Philosophically, all of them are values, but sometimes value is used as argument. So let's think about this like that. So we want to have notation now when by one letter x, we will mean in fact a vector which contains of three numbers and will represent a point in space. So now our x will represent a point in space. We already did it here. F represent a vector of force. Now, can we have a derivative of f with respect to x, and what that would be? You remember the definition of derivative. If we have usual function which maps r into r, the definition of derivative is a limit for some delta t which converges to 0 from f of t0 plus delta t minus f of t0 divided by delta t, if that limit exists. This is a derivative of function f at point t0. But we can't exactly do the same operation because we don't know what does it mean, and it doesn't have any good definition. What does it mean to divide it's not plus but minus. What does it mean to divide vector by vector? We don't know. We really don't know, and that's why this kind of definition doesn't make sense. But we might formulate it in a bit different way. So remember, this is vector, this is vector. If we will write this in this notation, remember, force depends on position in space, and with x0, with delta x, we understand vectors in space. So this is a position x0 with a small shift delta x, which also happens to be a vector in space, minus force in point x0. So this is a small difference of force when we move from x0 to x0 plus delta x. And now we want to have a which multiply by delta x will give us a good approximation of this difference. And the smaller delta x is, the better is approximation. So what a can be? A can be, in theory, a real number, because you can multiply real number by vector. But that will mean that this difference of force needs to be only in the direction in which we moved. So if x0 is here, imagine this is space, and delta x is a vector which shifts us to the point x0 plus delta x. If A would be a real number, that would mean that the change of force must be always proportional to the direction in which we moved. But force here might be like this. In x0, and in x0 plus delta x, it might be just longer. So the force here is stronger, but the change of force was in that direction, not in that direction. So that's not a good idea that A will be just a real number. So what is the entity that we can act on vector and multiply it? It is a matrix. If delta x is some shift vector, and we want also this to be a vector, and a vector of arbitrary direction, because we might define this force field as we want. So the small change when we move from x0 to x0 plus delta x, the change of force might be in arbitrary direction. So we want the result to be also three-dimensional. So what is the matrix that we can multiply column vector and get also a column vector of size 3, of dimension 3? Well, it's 3 by 3 matrix. So if A will be a 3 by 3 matrix, and we will act with this matrix on column vector. Oh, it's 2, sorry. What are our rules of multiplication? Row, first row, and first column, and we multiply them y by 1 and add them. I will write it explicitly. We take second row, first column, because we have only one column. And we take third row, first column. So in effect, as a result, we have also three-dimensional column vector. So now we can approximate our difference with matrix acting on our shift vector. Review once again this reasoning. We have a definition of derivative with regard to one-dimensional argument, and we understand it because we can divide number by number. If we want to apply the same definition for function, which is a function with vector arguments and vector values, we suddenly realize that we don't know what does it mean to divide vector by vector. And we really don't know it. It doesn't make sense to divide vector by vector. It might have sense if the vectors are directed in the same direction. But if the directions are different, what does it mean to divide vector by vector? But we can write it as multiplication, which we understand because we know how to multiply matrices, and obviously our vector is column vector, so it's just a matrix of dimension 3 times 1. And we use derivative as an approximation of difference of values when we shift a bit from our point x0 to the point x0 plus delta x. And this difference of values of force might be in arbitrary direction. So this is only matrix, which 3 by 3, which can give us an arbitrary direction as a result of multiplying by our original shift. So this is the concept of derivative of the multi-value function, which has multi-value argument. Now, if we know that derivative of force field is a 3 by 3 matrix, we can ask a question: what exactly are elements of this matrix? And the answer is very simple. We will not prove it here, but we will give you a formula, and I will show you how to memorize this formula. So let's first rewrite this. So in given point x0, when we did a small shift of delta x, we have difference in force that we describe in a good approximation by matrix A multiplied by this small shift vector. Now, by convention, we denote matrix A as derivative of f with respect to x, where x is understood as our three-dimensional argument of f, or vector, three-dimensional vector. So we can write this. In fact, you can use approximation if you are not comfortable with equality sign here. We can use approximation, but this is not that we are defining anything here. We're just trying to conceptualize things. By convention, we denote A as derivative of f with respect to x. I will remind, x is a three-dimensional vector. But what this matrix really is, we will give a formula here. You remember, f is composed of three values. Each of them depends on position. This matrix is simply I will use eraser here because I will need a bit so you see that we write here each combination of partial derivative. We introduced a bit earlier, if you remember, when we had real value which depends on three arguments, we introduce a concept of partial derivative, which is simply a derivative with respect to one of these variables. So here we can have these three partial derivatives. So if now our force function consists of three values and each of them depends on three values which are our point coordinates, then each of these component values can have three derivatives with respect to each of these coordinate values. That gives in total 9 possible partial derivatives, and if we put them in that order, that constitutes exactly the matrix A which is approximating this difference, and that's why it is derivative. Now, what is a problem here, and it was always a problem for me, is how to remember where we put functions when we put the same function of this tree and when we put the same variable. The technique to remember it is to associate in your head that what is up is connected to column vector, what is down is connected to row vector. And that's a convention which will be used later when we will talk about tensors. But for now, just associate this in your head, that up is column, down is row. So if we will note very symbolically column vector of forces, but this is just symbol like partial derivative of force, and then it will be divided in quotation marks by partial derivative of position of argument vector. And then we will multiply them exactly in a way as we multiply matrices. So then, how we multiply matrices? We take first row, first column, and we put a summation of multiplication, which will be only one element now. We take first row, second column, we take first row, third column, and so on and so on, and we will just get this matrix. This is just a way how to memorize it. You need to first do some kind of association in your head between things which are up with column and things which are down with row. As I'm saying, that is useful convention which will be used later, but for now we will not talk about this. And then you will do multiplication of that vectors of some sort. They are highly abstract vectors, and multiplication is just a formal, very formal multiplication of this symbol times this symbol, so we will get this symbol. But in effect, we will get all derivatives, all partial derivatives, in an order that we need. And obviously, we can do this for arbitrary functions. You might have as many dimensions of the value as you want. You can have as many dimensions of the argument that you want. The rule how to create this derivative is always the same. So we can now write a derivative of multi-dimension function with respect to multi-dimension argument as a one very compact term. And this is very useful because when we have let's our f be still a force dependent on three so three coordinates of force vector depends on position, which means three coordinates of position. And then let's assume that for some reason we have not like that, sorry. Let's assume we have a again some kind of movement function. It doesn't really matter, that will be arbitrary situation. I forgot, I want different convention here. I don't want to use x, y, z because x will be our vector argument. So that will be x1, x2, x3. This is just position of our of some particle in space depending on time. So now if we have a force field, which means force, vector of force which depends on position, we can say what is the force acting on the particle at each point of time. And then we might want, for some reason, calculate a derivative of f over time. So how to do this? What is amazing the chain rule holds. But only when we remember that this is a matrix and that will be a vector, and this is matrix multiplication, which in that context means matrix times vector. What vector that will be if x is x1, x2, x3? Obviously, it is a very intuitive and also it's according to the previous definition, but it's a bit tricky to notice that our derivative with respect to t is also a column vector. Simply derivative calculated at each coordinate. Let me improve a bit the look of this vector. And this is the matrix which we know how to write. So we can now change this very compact expression into a longer one in which we recognize our chain rule, which was introduced a bit earlier. So let us write again our derivative with respect to x, remembering that x consists of three numbers. Now we will act with that matrix on this vector, or multiply. It's sometimes we say act, sometimes we say multiply. It will become clear at some point why we say act. Right, and now let me erase this now, because anyway we have this here. So now, what is the result of this? It will be again three-dimensional vector. We take first row, first column, multiply and add accordingly. That's only one variable here, so we multiply this by this, now this by this. We are in the first row, so we are taking first row from first matrix, first column from the second. Let's pause on this. What is this first value here? It reminds us something. It is a chain rule for a function which depends on one argument but has only one value, one-dimensional value, right? We took all possible partial derivatives, multiplied them by derivative of argument with respect to time, and add all together. And this happens to be just a derivative of f1 with respect to t. And we can do this for each row but you already see the rule. So again, chain rule written in this longer form of adding multiplications. Of the second component of force. And now we take third row, first column, and go from the beginning, partial derivative of f3 over x1 oh, it's x2 here. Sorry. It's this element times this element. Again, chain rule applied to third component of the force vector. So we can see how compact this notation is. This means the same if we know what derivative of f with respect to x is, and if we know what is derivative of a simple vector functions of one argument, but this is a very intuitive what it is. So, can you now see the picture of this lecture? First, we introduced matrices. You get used to operations on matrices. Now we showed in what sense derivative is matrices, and the sense is, as we formulated it together, that we use derivative to approximate a small difference of function values. And this is exactly how we approximate it. Let's say we will use approximation symbol. With matrix acting on vector. So we introduced what does it mean that derivative is a matrix. And then knowing that it is a matrix, we can express chain rule in a very compact expression.